Welcome to the Book Doctor Technologies, your ultimate guide to SHS mathematics.
Welcome to SHS Mathematics. This is the first lesson in the series. First strand, number for everyday life. We shall begin with the first substrand, that is real number system. Real number system. By the end of this learning, this studies, or this encounter, you will develop the real number system using the closure property, distinguish between rational and irrational numbers, using conversion of common to decimal fractions, and solve related problems. Establish the properties of real numbers with respect to commutative, associative, identity, inverse, distributive, and etc. Review the properties of subsets, both 2 and 3, their vocabularies and operations, and use it to solve real-life problems. We also look at organizing information visually to establish the relationship between and among sets of items, both 3 sets and then 2 sets, and apply this conduct in mini surveys in the school, community, and beyond. Establish the relationship between and among sets, including the set equations and the De Morgan's law. Let's start the ball rolling. Let's look at some history of the development of numbers. In ancient times, man began to count. They counted using their fingers or making marks on walls, and then creating notches. When counting became complex, they began to use symbols such as the Babylonians, the Indians, and the Egyptians. The Romans also developed their system of numbering. But the most commonly used numerational system is the one that is developed by the Hindus, which was propagated or spread by the Arabics and is known as the Hindu-Arabic numerals, or for short, the Arabic numerals, where we have digits from 0 to 9. 0 to 9, the most common one. 0, 1, 2, 3, 4, up to 9. And any other number is formed based on the combinations of these numbers. It is very common to us. We've been introduced to these numbers right from our basic school. Good. Now, let's move ahead. Numbers can be broadly grouped into 2. We have the real numbers and non-real numbers, or numbers that are not real. Non-real numbers. Real numbers are all numbers that we can represent on the number line. All the numbers that can be represented on the number line. It includes fractions. It includes whole numbers, negative numbers, and etc. Every numbers that can be represented on the number line are called real numbers. From your study of mathematics right from the basic school, kindergarten, primary, junior high school up to the SHS, the numbers you have been introduced to are real numbers. And in the senior high school, we only mention non-real numbers to you, but will not be treating non-real numbers. You treat non-real numbers when you enter the universities. Non-real numbers are imaginary numbers, numbers that cannot be represented on the number line. We have the imaginary number, mostly denoted by the letter I, and then we have complex numbers. These numbers are not real, and as such, cannot be represented on the number line. So we will focus our attention on the real number system. The real number system. Real numbers can also be broadly grouped into two. We have rational numbers and irrational numbers. Irrational numbers. Rational numbers and irrational numbers. The numbers that can be represented on the number line can be grouped into two. The rational numbers are numbers that can be expressed in the form A over B. Any number that can be expressed in this form is known as a rational number. Irrational numbers, however, cannot be expressed in the form A over B, cannot be expressed as or in the form A over B. That is the only distinction between rational and irrational numbers. So we have numbers such as the whole numbers, which we know from the primary school, which we shall go over again. Whole numbers, integers, a set of integers, etc. Certain fractions, certain decimal fractions, or let me just put it, terminating and recurring decimal fractions are all belonging to this category. When we come to the irrational numbers, we have the sets. Sets includes something like the square root of 3. That's the square root of non-perfect square. The square root of 5. The square root of 11. The square root of, let's say, 19. The square root of 21, etc. All these numbers are irrational. And we have non-terminating decimal fractions. Non-terminating, non-recurring. If you have a decimal fraction, for example, 2.13456 2148, etc. It doesn't terminate, and neither does any pattern repeat itself. Then we call it an irrational number. Non-terminating, non-recurring. Remember, when the fraction is recurring, then it is rational. For example, if I have 2.66666, this number, which is recurring, can be expressed in the form A over B. It is not terminating, although, but it's recurring. Or, for example, 2.121212. This is a recurring decimal fraction. It doesn't terminate, but it recurs. There is a pattern that repeats itself. When it happens like that, it is a rational number. We can express it in the form A over B. Irrational numbers, however, when it is in decimal form, there is no pattern that is repeating, and the decimal fraction does not terminate either. So let's take note. So the clear distinction is that for rational numbers, we can express them in the form A over B, but irrational numbers cannot be expressed in that form. So in the next minute that follows, we shall zoom in into rational numbers and look at the various numbers that, or groups of numbers that form rational numbers. Rational numbers can be grouped into two. We have the set of integers, always denoted with the letter Z, and fractions. Fraction may include vulgar fraction, recurrent decimal fraction, terminating decimal fraction, percentage fraction, and etc. And then, when you combine these two together, the integers and the fractions, they all form what is known as the rational numbers. So this is the composition of rational numbers. Rational numbers are always denoted with the letter Q, and integers with the letter Z. Now let's zoom in into integers. Integers. So integers has two categories. We have the negative integers and the whole numbers. Negative integers and whole numbers. Negative integers are numbers that are less than 0, and the whole numbers are numbers. Whole numbers are numbers that begin from 0 upwards, 0, 1, 2, 3, and etc. Then when we pick whole numbers, we can group whole numbers into two. Whole numbers can be broadly grouped into two. We have 0 standing alone and natural numbers. Natural numbers or counting numbers. They begin from 1, 2, 3, 4, etc. So when we add 0 to natural numbers, we get what we called whole numbers. The natural numbers are also known as the counting numbers. We can also group the natural numbers into three broad regions. One standing alone, then we'll have prime numbers. So one is standing alone, then we have prime numbers, then we have composite numbers. One has only one factor. Prime numbers has exactly two factors. And then composite numbers have more than what? Two factors. So based on the number of factors that a number has, it falls within this three categories. Being one standing alone, a number can either be prime or composite. A number can also be prime or composite. We can also classify numbers as to whether they are divisible by 2 or not. Numbers that are divisible by 2 are known as even numbers, and those that are not divisible by 2 are known as odd numbers. Remember, even numbers are numbers that are divisible by 2. So that, by that definition, 0 is an even number. Even numbers, when you are listing even numbers, we start from 0, then 2, 4, etc. Numbers that are divisible by 2 are even numbers. It includes 0 because 0 is divisible by 2. Closure property. Closure property. The closure property of a set states that if you pick two elements of a set and they undergo an operation, and the outcome is also an element of the set, then we said that set is closed under that given operation. Let's look at an example. When you have A, which is a set, which has the following element: 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Let's test addition. If we pick any two pairs of numbers and we operate them under addition, and the results can be found under this set, we say that this set A is closed under addition. The operation should work for all the elements of the set, not only selected few. For example, we know 1 plus 4 will yield 5, and 5 is an element of the set A. But you don't conclude that addition is closed under this set A until you have exhausted all the possible combination of the element under A. So for instance, 9 plus 10 will give us 19. 19 is not an element of A. It's not an element of A. And as such, we cannot say that the set A is closed under the operation addition. We would like to subject the closure property to the set of numbers we have learned today. First, we'll pick the set of whole numbers. We know whole numbers are numbers that begins from 0, etc. We'll subject this under the 4 basic operations: addition, subtraction, multiplication, and division. We would like to find out when two numbers undergo an operation under these operations, the outcome will be an element of this operation. An element of this set, whole numbers. So we are going to pick first addition. Addition. If we study the addition table carefully, or the addition of numbers, when two whole numbers are added, the result will always be an whole number. 0 plus 5 will give us 5. 5 is a whole number. 20 plus 500 is 520. It's a whole number. Any two pair of whole numbers that are added, the results will be a whole number. And as such, we can conclude that addition is closed under the set of whole numbers. Let's look at subtraction under whole numbers. We know whole numbers begin from 0 up to infinity. Can you see that subtraction is closed under whole numbers? Can you guess the answer? No. Subtraction is not closed under whole numbers. For instance, if I have 10 minus 20, the answer is negative 10. And negative 10 does not belong to the set of whole numbers. And as such, we cannot conclude that subtraction is closed under whole numbers. We shall look at
another operation. Multiplication. Multiplication. Can you pause the video and guess whether multiplication is close under whole numbers? If your answer is yes, then it is true. When you multiply any two pair of whole numbers, the result is also a whole number. For instance, 5 times 100 will yield 500. 500 is a whole number. There is no two whole numbers that will multiply that the result will not be a whole number. The product of any two whole number is also a whole number. And as such, we can conclude that multiplication is close under the set of whole numbers. We shall now look at the operation division. What will be your guess? Is division close under whole numbers? If your answer is no, then you're right. It is not always that when you divide a whole number by another whole number, the result will be a whole number. Even though, for instance, if I divide 10 by 2, the answer is 5, which is whole. If I divide 2 by 10, the answer is 0.2, which is not a whole number. So, as such, division is not close under the set of whole numbers. We shall now pick another set of numbers and look at whether they are close or not close under the four given operations.
In summary, the properties of closure on whole numbers is shown. A whole number plus a whole number will always use the whole number, so it's closed. A whole number multiplied by a whole number will also yield a whole number, so that is also close. But under subtraction, a whole number minus another whole number not always will it yield a whole number, so that is not closed. So subtraction is not closed under whole numbers. Then a whole number divided by another whole number, the result is not always a whole number. So division 2 is not closed under the set of whole numbers. We'll now look at the closure property on integers. On integers, we'll subject it under addition. An integer plus another integer will always yield an integer. There is no two integers when added will not yield an integer. And as such, addition is closed under integers. Then multiplication. When any two integers are multiplied, the result is always an integer. For instance, -5 multiplied by 10 is -50, and -50 is an integer, is a negative integer, and as such, multiplication is closed. under integers. Then we'll look at subtraction. When two whole numbers are subtracted, the result is always an integer. For instance, 6 minus 2 will yield 4. 4 is an integer. And 2 minus 6, the result is negative 4. Negative 4 is an integer. And as such, subtraction is also closed under integers. The last operation we shall look at is division. Division is not closed under integers because an integer divided by another integer will not always yield an integer. For instance, 5 divided by 3. The result is not an integer. This will yield a decimal fraction. We know fractions are not integers. This is 5 on 3. Or otherwise, one whole number, 2 on 3. Or otherwise, 1.66 recurrent. This is not an integer. And as such, division is not closed under the set of integers. In summary, this is the table displaying the property of closure on the set of integers. As indicated earlier on, aside division, the other operations are all closed under the set of integers. We shall also investigate the closure property on real numbers. First, we'll look at addition. When two real numbers are added, the result is always a real number. And as such, addition is closed under real numbers. Then multiplication. When two numbers which are real numbers are multiplied, the result is always a real number. We'll look at subtraction. When two numbers are subtracted, the results, if the two numbers are real, then the results will also be a real number. And as such, it is closed. Division. Division is not closed under real numbers. Can you tell us why? When any two numbers which are real are divided, the result is always a real number, but not when the first number is 0. For instance, when the divisor is 0. So for instance, 2 divided by 0 is undefined in mathematics. We cannot divide any number by 0. is undefined. So 2 over 0 does not yield a real number. Aside the situation whereby the denominator or the divisor will be 0, all other divisions are possible. We can divide any real number but by another real number except 0, and the results will be real. So since 0 is a real number and it is part of the set of real numbers, the closure property will not work under division. Remember, we said that the closure property should work for all the elements within that particular set. And since 0 cannot divide any real number, we conclude that division is not closed under real number. In summary, we see that real numbers, when you add a real number to another real number, the result is a real number, so it's closed. A real number multiplied by another real number, the result is a real number. As such, it is closed. But a real number minus a real number is also a real number, so it is closed. The subtraction, multiplication, and addition are all closed under real numbers, except division, which is not closed because we cannot divide any real number by 0. This session, we have looked at the numerical system, and we said the numerical system is made up of real numbers and non-real numbers or imaginary numbers. Under the real number system, they are grouped under rational numbers and irrational numbers. And we said rational numbers are those that can be written in the form A over B. And irrational numbers are numbers that cannot be written in the form A over B. They include square root of non-perfect numbers and the pi. And the rational numbers, they are grouped into 2 categories: integers and fractions. Fractions could be vulgar fractions, recurrent decimals, and terminating decimals. The integers is grouped under negative integers and whole numbers. Whole numbers consist of 0 and the natural numbers. And we also group the natural numbers under 3 categories. And this is 1, composite numbers and prime numbers. In the next section, we shall look at ways of describing sets. Thank you very much, and don't forget to subscribe to my channel.